Hello students, in this tutorial we are going to discuss example 2 of principle of mathematical induction. Here we are going to prove that 2 raised to n is greater than n for all the positive integers. Here is the inequality given. Let us see how we'll show the proof. So the solution, let the given statement be P of n. We always start the proof by naming the given statement, that is P of n. So P of n is 2 raised to n, which is greater than n. So now the step 1. In step 1, we show that the given statement is true at least for the first natural number. So let us verify the given statement for the first natural number, that is for n is equals to 1. Let us take the statement 2 raised to n is greater than 1. Replace all the n by 1, that is 2 raised to 1, which is greater than 1. What is 2 raised to 1? It is nothing but 2, which is greater than 1. So 2 is obviously greater than 1, isn't it? Yes. Therefore, P of n is true for n is equals to 1. Therefore, the given statement is true for first natural number. Okay, in the step 2. In the step 2, what we have to assume is, we have to assume the statement is true for other natural numbers also, and let that be k. If the given statement is true for first natural number, then we have to assume that the given statement is true for other natural numbers also, and let that be k. Okay, so all the n we have to replace by k. So here p, this n will be replaced by k, and 2 raised to n, this n is replaced by k, which is greater than k. Okay, let this equation be 1. We keep this handy for our third step, isn't it? Yes. So next is the step 3. Now we need to prove that P of n is true for n is equals to k plus 1 also. Now when we assume that the given statement is true for some natural numbers, then we need to prove that the given statement is true for the next natural number. Suppose if we have considered the k here as 70, then it should be true, the given statement should be true for 71 also. If k, suppose if we have assumed here as 82, then we have to prove that the given statement is true for 83 also. Understood? That's what the statement means here. That's what it means. N is equals to k and n is equals to k plus 1. So what we do now, we replace all the n by k plus 1. So here all the k are getting replaced by k plus 1. That is 2 raised to k is getting replaced by 2k plus 1. It is greater than this k is again replaced by k plus 1. Now we need to prove that 2 raised to k plus 1 is greater than k plus 1. Students, if you recall, in the previous example, we have substituted the value of p of k in here. And we always do that. We usually substitute the value of p of k in p of k plus 1. But here we cannot substitute the value because of the inequality here. There is a greater sign instead of equals to. Therefore, we cannot substitute the value here. So what do we do now? Try to remember, students, in the inequality problems, always we take p of k and we prove p of k plus 1. Please try to remember this, that in inequality problem we take p of k and we prove p of k plus 1. Next, I have taken this 2 raised to k, which is greater than k. This is from equation 1. Sorry, this is inequality 1. So we ultimately need to prove that 2 raised to k plus 1 is greater than k plus 1 from p of k. So now we need to make 2 raised to k which is greater than k exact picture of 2 raised to k plus 1 greater than k plus 1. So we need 2 raised to k plus 1 here and not 2 raised to k. So how do we get 2 raised to k plus 1 here? Suppose if I multiply 2 on both the sides, will I be able to get 2 raised to k plus 1? Let's check. So I have multiplied 2 here on both the sides of the inequality because I have to get a 2 raised to k plus 1, isn't it? Yes. So let us simplify this further and let us see what we get. After multiplication, we get 2 raised to k plus 1. 2 raised to k plus 1 and 1 plus k is one and the same. As I want to get k plus 1 here, so I have written 2 raised to k plus 1, which is greater than 2k. But here I want to prove that 2 raised to k plus 1 is greater than k plus 1 and not 2k. Let's see how we get this. Let me write in this fashion. Let me split this 2k. Okay, I write this 2k in this fashion because I need something like this k plus 1, but still I'm not able to get k plus 1. So what we do now? Let us apply some logic here. If you look at here carefully, 2 raised to k plus 1 is greater than k plus 1. This is also greater than k plus 1. I'll explain you why. Let us put any natural number in place of k. We cannot put 1 because in the first step we have already proved that the given statement is true for the first natural number. So we cannot put 1. So let us start from 2. Okay, see here, I'll explain you this term. Let us put 2 in place of k, okay, and let us check. 2 raised to k plus 1, you put 2 in place of k. That is k plus k, 2 plus 2, k plus 1, 2 plus 1. So what we get is 2 raised to 2 plus 1 is 2 raised to 3, which is greater than 4, and 2 plus 1 is 3. So 2 raised to 3 is obviously greater than 4, isn't it? So if 2 raised to 3 is greater than 4, then 2 raised to 3 is obviously greater than 3, isn't it? See here, if 8 is greater than 4, then 8 is obviously greater than 3. That's what I told you. 2 raised to k plus 1, which is greater than k plus k, is obviously greater than k plus 1. So therefore, we can conclude that 2 raised to k plus 1 is greater than k plus 1. Therefore, p of k plus 1 is true whenever p of k is true. So therefore, by PMI, the statement is true for all the other natural numbers. Thank you, students.